high school.
That's a nice what? Oh, thanks. All right, so I like to set up the diagram and I always do F graph since it's always there. And then we are given 300 kilograms for the mass. We have mu at 0.800 and acceleration. Squared. Okay, so we know that our verticals are going to be balanced. And it's on the ground, so we automatically have an F norm. And it tells us we have an applied force, because that's what we're looking for. And we have a coefficient of friction, so we know we have friction. All right, so I always start with F graph because I feel like it's really easy to find, which is going to be your mass times gravity. So we have 300 times 9.8, which gives us 2940. And I think it's always super easy to fill it in on the diagram too. Then from there, we have mu. So we know our up and down is equal because those are balanced forces. So we know that our F norm is going to be the same as the F graph, which is 2940. And then from there, since we have a norm now, we also have mu. We can find F friction, which is going to be 0.800 times our 2940. So our F friction will be 2352. And then now we know that our horizontal forces are going to be unbalanced. So we would use our sum of the forces equals mass times acceleration. And I always write this out here just to keep myself on track. So again, we have the 300 kilograms mass, and we're given an acceleration of 0.580. Which ends up at 174. And then I really like the winner loser thing that you do. So we now have our 174 is going to equal the F applied minus the F friction, because we know the applied is going to win because we have an acceleration on the applied, so loser. And we're given, well, we found, excuse me, the friction. So to solve for F applied, we add those two together. Since it's over here, we move it across. 25, 26. So 26 newtons. That's it.
Questions for Gary?
Okay, actually, never mind. I answered that question.
Sure.
Because I like the S gravity, that I don't like the way I like write it. I just always put like gravity and like I leave it and like the F arm is gravity with the statement 40. And like I just got confused with it, but I didn't see put on the norm. I just said put on.
Oh, got you. Yeah, so I did it over here because we have our mass times the gravity.
And then like I would just do like F arm. Some gravity so being like F gravity being mass times gravity. I would have.
Could you repeat what you said to where you knew what Natalie said about how she knows that F norm equals to mass times gravity? Say earlier.
F norm is equal to mass times gravity. Oh, because our vertical forces are balanced.
So now because the vertical forces are balanced, the up is equal to down. And from your diagram, you said you did what? Like with your diagram, I just really what?
Oh, the F norm and the F graph.
Yeah, so now that you
Yes.
know that both fields are equal to each other, to where then you can solve.
Right, because we're trying to find the horizontal force. And we know that they're unbalanced because we have friction over here and there's an acceleration.
I would say for me, I mean, can y'all see the board online?
Yeah.
Yeah, like I would say, like just from a standpoint of just trying to solve a problem, it should look like this. Like as detailed to where even if, let's say she did, because she has the right answer. Let's say if she was to do like a small miscalculation with some math, I still could follow it because I could see where she labeled it. She said my up equals my down. So what does that mean? Okay, I have these two forces that I want to compare to each other. All right, I could do that. Let me see where she put that at. She said we have unbalanced forces. Oh, that leads to me having this winner minus loser thing over to the right. Okay, I can go back and track that. Like you want to have it as detailed as possible, so that way somebody else can follow your work and maybe be able to contribute or something. Like maybe Peter sees something, he's like, yo, what if we add tension somewhere? Let's see how it goes. All he has to do is just add something right to the free body diagram instead of him having to come up with something new. Like he already builds off of what you have. So like being this detailed and kind of working through it is the best way to go with this problem. So good job, Carrie.
Thanks.
All right. Now you see Carrie volunteered herself for the first one. Would anybody like to try number 2? Anybody? I'll give it a go. I'll give you your paper back. Gotcha. You also get a color change. Oh, if you like. If you can, just make sure you speak loud enough so I can hear you online.
So first, I drew a field house. I drew like a house. That just makes it easier. And then I kind of just do it based on how like I visualize it. So I did started off with the base first for how far the ball traveled. We do 33, 4, 9 meters from the house. And then at the top, I put how fast the ball was kicked. So that's 15.8 meters second. And then kind of like try to draw a triangle first, but obviously it's a little bit round. And then I just like the force of gravity always. So starting off from here, you know how far the ball went and at the acceleration it went, or at the velocity. So it to 33.9 meters over the 15.8 meters per second to find out how fast it's going per second. And then that will equal to our time. And then from there, we're trying to figure out the height of the house, so the displacement, which is going to be half of the gravity. I kind of do it, and then time. Oh, so the way I do it, I kind of just already know that half of gravity is 4.9, so I just skip to 4.9 times this what we already have, the 2.1 squared, which is going to equal to 4.9 times 4.41. And then that's going to equal to approximately 21.609 meters. And then from there, we just round up to around 22 meters. And then that's gonna equal our height. 20, approximately 22 meters for the height.
Any questions
Any
for Zoe? I have a question. How did you know for the displacement that you could use the equation of 1/2 times gravity times time squared?
Honestly, I remember it from our last class or when we were going over this equation. Because to me, I like prefer. I'm like good at math and I like math, but I prefer like simpler equations because I feel like I can skip steps more easily. So I like starting off with like just this. My brain would automatically just go here.
Mhm.
So I wouldn't do necessarily all of these steps. It just goes here. So I kind of just like to maximize my time, I guess. So like with this equation, like I said, like because this is like an automatic, like I already know what that is.
Mhm.
Like to me, like displacement, like the easiest way to like get to here is to like kind of like skip that step. Just because there's so many like equations and like different variables that we need to remember. I kind of just like always try to remember. Like to me in my head, like this is always just gonna be kind of like the displacement, right? Is always gonna equal 4.9 times like the time. I'm not good. I like don't think half of gravity. I just think 4.9.
Okay.
Does that make sense?
Now take like 2 steps back because this is for a specific case, right? Because we actually use one of the kinematic equations to walk it down to get to this. What specific scenario do we use this equation for? Does anybody remember? Starts with an F.
Like the free fall.
Free fall, right? But that free fall comes from when a volunteer, somebody volunteered somebody who had to see it on their paper right here. That just went last time. What did you write on your first part of your equation for this problem two?
The change the displacement on the y-axis.
On the y-axis, right? For you to get to this point, to get this equation, you had to make an assumption. What did you assume?
Just that gravity will be present. That's going to be our acceleration.
Well, fourth thing, it's free fall. So what else do you know?
The initial velocity, I assume, would be 0.
The initial velocity is 0. So then when you start off, you actually start off with the first kinematic equation. Here, where you know the displacement is equal to the initial velocity, let's say the y, times the time plus 1/2, technically whatever acceleration that is, times time squared, right? So we get here, we know that the initial velocity is going to be 0 because we're in free fall. So we got 0 times time plus 1/2 acceleration, which we know is what? Acceleration due to gravity, 9.8, right? So this is where you get your 4.9 from. This is 0, so all of this becomes, so now we have 1/2, 9.8 here, which then turns into 4.9. So this is the case for free fall, right? But where does it come from? It comes from this initial kinematic equation, the understanding the fundamental principle that in the y of free fall motion, the initial velocity is 0. So just know where this comes from when you plug it in. If you think free fall, now if you're a math person, if you hear free fall, oh, you can automatically jump to that, yes. But just know in general, where does it come from there? Just so that you can be able to put it back. But in the reverse part, taking it back from the actual answer, I see a diagram that I can follow. It's very much labeled. I see the first step, which is finding the time, and I can see that we have an equation for free fall, right? So I can go in, ask my questions, add to it, make suggestions if needed, because we're still getting to the point where we're very much getting more detailed. So good job. That's like that. Appreciate you. All right. Doing good. See, anybody have any questions online? Okay, no. We got one more problem. Anybody want to volunteer for the last problem? So confident. Or volunteer. Either one. Or do we want a tag team? I think we'll do a tag team. Someone down. What color you want? Green.
All right. All right, go ahead.
I'll just speak loud so everybody can hear you online.
So mass is given 1 kilogram, and it says that the cable makes a 1 degree angle with the horizontal, so it means that the degree is 1 degree. So there are 2 forces acting on it, where so we have to plus these 2 together, and then we'll get since the 2 forces are balanced, so it will equal to equilibrium. Then we have to find T. We have mass, we have gravity, which is 9.8, and that's basically it.
Any questions for Seth, right? Any questions for Seth? Anybody online? I got you.
I can't really see the board.
Better, worse,
Maybe closer.
better, worse.
the reflection from the light is making it hard.
How about that?
That's a little better, but the marker is also super light, I think. I don't know.
Yeah, maybe a darker lighter marker.
One thing I will say that I want to point out, you did a good job of pointing out like the forces and how they correspond with each other. But for a problem like this, I would definitely want to make sure that we just at least add the vector diagram. Only so you can see where it all comes from, right? So now we have let's say our cable holding it up, right? Is joined together by two.
We can't see.
See this?
No, the board's too high.
The top half of the board is cut off.
Right here. See that?
Yeah, that's visible.
So we go here, right? So this say like this is the cable holding it, right? It's together by two vectors. Oh, I didn't mean to do it like that. Sorry. A horizontal and a vertical. We know that this one really is the tension that comes from the cable, right? Let me do it like this. Still the same force. Makes sense. I'm just changing the directions. Because you want to pull up. Right? When we break this down, we know that we have our two components, FTY, and then the tension in the X. We're able to figure out by the free body diagram here that, yes, there is a tension force that's here, right? Both sides. And that force counteracts gravity. So this is an equilibrium state, right? Imagine these are the same size. T. Right? So we know that this up part is going to be the same as gravity for the equilibrium. So now we can say that this is also equal to 1/2 gravity. So now when we do this triangle, we can actually make this a value. So whatever he just said it was here, 1 kilogram, now we can actually put this here as basically as 0.5 times, 1 times 9.8 divided by 2. So that's about 4.9. What I say that to say is, though, include the vector triangle diagram so that we can see where we get the actual mathematical calculation. Because now when we look at this, if we want to find this and we have this, we know we can use sine of the angle equals to opposite over hypotenuse. And that's where all of this comes from. Because we see that we have the opposite and we want to find the hypotenuse and we have the angle. So this, I know, Courtney, you were saying earlier with the triangles, this is where we start to use it when it comes into the forces. Just taking it from the free body diagram, pulling out the triangle here and bringing it over here so that we could do some trigonometry.
Yeah, that's the part that I struggle on right here. It became very frustrating.
Got to work at it. But this is where it's used at. Hopefully, I'm going to put this up so that you can go back and see it too, along with the stuff that we've done before. But really, right now, just practice.
I found a really cool way that might be helpful if you don't mind looking at my paper again. I found it was actually ChatGPT that showed me that when you get the sine of 1 and it's 1.7%, you multiply that by your result and it'll help you check your vertical because you'll come out to 4.9.
Did you hear that helpful tip from Carrie?
I think it's easier than the trig part.
Where did you say you got it from?
Chat GPT.
There we go. So she used the resources. I am not opposed to using ChatGPT or any AI tools to help you figure things out. I actually want you to be resourceful. Whatever you have to do to get this, please do it. All right. Give me 5 minutes. Because I was taking a little bit of time, but I did like how you guys did that. But this is just so I can introduce momentum so you can at least know what we're going to cover mostly on Wednesday at 7 online. So Wednesday we'll be online at 7. We'll go through this and then we'll be back Monday in person. But if you are able to join real quick, if you're not already on, because I have slides, just join in like 2 seconds. Oh, wait. Y'all in person. For my people online, just look at the slides. If you're in person, you don't have to join online. Just grab packet 5 that I just gave you and just look at it. And just look on the first page. So some things to go over. Share screen. Hold on. So now we are into Unit 5, which is momentum, collisions, and collisions, right?
We can't see your screen.
Do you see it now?
So
What about now?
no.
I can see it. The PowerPoint, right?
Yeah.
Yeah, I can see it.
Try and refresh it.
Okay.
All right. So now this is our end goal, right? We want to be able to solve a simple bowling ball problem, right? We want to be able to determine how fast a bowling ball moves after it's being impacted and using these basic concepts that we know about momentum, right? So if we're able to be able to calculate how fast a ball moves off of just a little bit of information, then we reach our goal for the end of this unit, right? So that's the type of problem we want to be able to see how far a ball goes in a stationary thing. So just a very simple example of that, right? So how we get into it, these are the different topics we're going to talk about, right? And the first one we're going to really dive into really is talking about momentum and impulse and momentum and change, right? So kind of figuring out what these things are and then playing around with them and seeing how they come as one full topics, right? And then that'll get us to our bowling ball problem. So the first thing to understand right now with momentum, right? What is momentum? Think about it as mass in motion, right? Something's moving and then it has this thing we call momentum, right? That goes with it to where now you see it's moving and we can kind of predict how far it's going to go. And then later on, you'll see with impulse, we can see it has some force attached to that, right? But really, momentum is equal to an object's mass times its velocity. So it's very simple, right? Now, when we understand that momentum is equal to an object's mass times velocity, what does that say more about momentum, right? First, momentum represented with that P, right? So like usually a lowercase p, I should probably change that, is equal to mass times velocity. Because it's mass times velocity is what? Its units are now kilograms meters per second. So anytime you see kilograms meters per second, you should think about momentum. Next thing, because it's mass times velocity, velocity is a what? Scalar or vector?
Vector.
Vector. So therefore, momentum is also a vector quantity. So when we have momentum, right, we can't just say kilograms meters per second. We also have to have a direction to go along with it too as well. Lastly, this is the part that really is going to make sense as we get deeper into this topic. Momentum is conserved in the system, so it's not really created or destroyed, right? So understanding that in the system, it's never like it's going to just enter. It's just like always going to be what you have in your initial is going to be your final. So whatever momentum you have in the beginning before a car crash, you'll see it'll be the same at the end of the car crash. So things means inside of it is going to have to change. We'll see that in a little bit. Well, let's just kind of play around what we just went over with momentum, right? So identify the qualities that momentum depends on, right? So we have 5 different quantities, right? The momentum of the object depends upon the object's what? Mass, which is how much stuff it is, has acceleration, the rate at which it changes velocity, the weight, the force by which gravity affects the stuff to Earth, velocity, how much in which direction the stuff is moving, or position where the stuff is at. It's 2 answers. What 2 answers are we going with? Carrie said mass and velocity in person. Anybody else? Got another one, mass and velocity. Anybody just, okay, I see a light. Pretty simple, right? Momentum depends on an object's mass and its velocity. So how much stuff it has and how fast in which direction it's moving. Now, when we understand that, right, let's consider the momentums of the two objects, right? Compare them, right? So if we have the mass and velocity of the objects A and B below, right? Compared to object B, object A has a momentum that is what? 2 times, 4 times, 8 times the same, 1/2 or 1/4. So object A has a momentum that's compared to how much of object B? So object A has a certain amount of momentum, and then compared to object B, how much is it? Say it louder. You said twice as much. Zelly said twice as much. Anybody disagree, agree? I hear and agree. So we good. Now, why did you say twice as much?
I was trying to unmute my phone. Can you go back really quick
Which way?
to the one to the momentum right there? So why is it the first? Oh, okay. Mass, how much stuff it has. Okay. Okay, that's fine. I got that.
All right. Back here. Zelly, why did you say 2 times? So 4 is twice as much as 2. So like you said, you're a math person, right? Now, can you add the physics compass on to why 4 is more as twice as 2 matters? What is 4 and what is 2? The mass,
The
right?
mass.
There we go. Good. So object A has a mass of 4. Object B has a mass of 2, right? So we both know that they both have momentum. So momentum is equal to mass times velocity. Our velocities are the same, right? We see it's both 4, right? So the only thing that's different is the masses, and it's different by a factor of 2. So now we can say that the momentum will also be different by a factor of 2. See how that works?
So the answer is B. Oh, 2 times.
2 times. So A. Now let's take that, right? The last thing we'll do today, very simple. I just need you to calculate the momentums in each situation. Just for review, we know that momentum is equal to mass times velocity. So in the first one, A, right? We have a 2 kilogram brick moving through the air at 12 meters per second. What would be the momentum of that?
Who?
24.
Okay.
I heard it in person and I heard it online. Say it one more time.
12 times 2, 24.
12 times 2, 24, 24 kilogram meters per second. You do need a direction. It just didn't give you one. So we'll just assume we'll just be fine with the 24 for kilogram meter per second for now. But we do need a direction. So just keep that in mind. Second one, we got a 3.5 kilogram wagon moving along the sidewalk at 1.2 meters per second. What is the momentum?
.5 times 1.2.
Which would be?
Give me 1 second.
4.2.
4.2. I heard it in person as well, too. All right. How was that? Was that difficult?
No.
Okay, so with momentum, to be honest with you, a lot of the math is just like this, right? Now I'm gonna stop here for today. So now you understand momentum, right? When we come back on Wednesday, I'm gonna go over impulse and momentum change together, right? So what we just took from this, just digest it, come ready on Wednesday to understand impulse and momentum change and how they go together. And then we'll really start diving this unit. To be honest with you, this unit is not that long, so we might be able to finish this pretty quickly and then move along. So that's all I got for today. Any questions?
No.
All right. This will be on YouTube. So when I get in it, I have it, I'll put it together and I'll upload it. But other than that, I'll see you guys Wednesday online at 7.
Thank you.
See you. Thank you.
No problem.